Automation is often sold as a way to remove human error, but decades of research show something uncomfortable. Automation does not remove human error, it moves it. And the most dangerous moment is not when humans control everything, and not when machines do. It is when control is shared. To understand why, you have to understand how humans actually interact with complex systems. In fully manual systems, humans are constantly engaged. They feel resistance, notice anomalies early, and make small corrections all the time. Their skills stay sharp because they are always being used. In fully automated systems, humans are mostly removed from real-time control. The system is designed to operate independently or fail safely. Responsibility is clear. Either the machine handles the task or it stops. Partial automation sits in between, and that is where things start to break. In partially automated systems, humans are expected to monitor a system that usually works, remain alert despite long periods of nothing happening, and then instantly take over when something goes wrong. This expectation does not match human biology. Humans are extremely bad at passive monitoring. Attention decays when nothing changes. Reaction times increase. Situational awareness fades. This is called vigilance decrement, and it has been documented for more than half a century in aviation, medicine, nuclear power, and industrial control. When automation works well most of the time, people naturally trust it. That trust builds quietly. Cross-checking drops. Warnings feel like false alarms. When a real failure happens, the human operator is late, confused, and underprepared. This is not a training problem. It is a cognitive limitation. Automation also causes skill decay. When humans no longer perform routine tasks, their ability to do them degrades. Pilots who rarely hand fly lose fine motor control and recovery intuition. Drivers who rely on driver assist systems react slower in emergencies. Surgeons using automation may miss subtle warning signs when systems fail. The system improved overall safety, but it weakened the human fallback. Another major problem is mode confusion. Partially automated systems often have multiple operating states. The machine may be controlling speed but not steering, or steering but not braking, or following one set of rules under one condition and a different set under another. Humans are expected to track this invisible state machine in real time. In practice, they often do not. Investigations into aviation accidents, medical device failures, and autonomous vehicle incidents repeatedly show the same pattern. The human believed the system was doing one thing. The system was doing something else. By the time the mismatch became clear, there was no time left. This is why partial autonomy produces a paradox. As automation improves, total accident rates often drop, but the accidents that remain become more severe, more confusing, and harder to recover from. This is known as the automation paradox. The system removes easy failures and leaves only rare, complex ones. And those are the worst possible situations to hand back to a human who has been disengaged for minutes, hours, or years. You can see this clearly in aviation. Modern airliners are incredibly safe. Yet when accidents occur, they increasingly involve automation mismanagement, delayed manual takeover, or loss of basic flying skills. The pilots are not incompetent. They are victims of a system that asks them to be both supervisor and emergency backup at the same time. The same pattern appears in medicine. Automated monitoring reduces errors but creates alarm fatigue. Clinicians learn to ignore alerts. When a real alert appears, it is sometimes missed. And it appears in cars. Studies show that drivers using partial self-driving systems look away more, respond slower to takeovers, and perform worse than fully manual drivers in sudden emergencies. That is why regulators consider partial autonomy one of the hardest phases to certify and control. Full autonomy, paradoxically, is often safer in principle. The system is designed to handle everything within its domain, or to fail in a controlled way. Humans are not expected to jump in at the worst possible moment. Manual systems are also safer in a different way. Humans stay engaged, skills stay active. Responsibility is clear. Partial autonomy combines low engagement with high responsibility. It assumes humans can stay perfectly alert without action. instantly regain context, and outperform machines under stress. That assumption is wrong. Automation shifts human error from execution to design, supervision, assumptions, interfaces, and rare edge cases. The error never disappears. It just moves to a place that is harder to see and harder to correct. This is why many safety engineers say the most dangerous sentence in engineering is not "humans are unreliable," but "the human will intervene if needed." Because when that moment comes, it is usually already too late. Automation does not fail because machines are stupid. It fails because humans are human, and until systems are designed around that reality, partial autonomy will remain the most dangerous phase of all.